So this session is meant to go over some of the problems that you have been assigned, and it's for you to also ask me anything really that you'd like to see me go over again, either from the problems or from the lectures. For example, yesterday we went through Deutsch's algorithm, which is fairly complicated. So if you'd like me to, I can go over that, the calculations from Deutsch's algorithm again. So there are several things that we can do. It's a bit up to you. So maybe if you have any ideas, can you suggest this in the chat? And then we can decide what to do. Can you go over Deutsch's algorithm? I can do that. Let's see if anyone has suggestions, more suggestions. Same, yes, please. Oh, good. Okay, awesome. Yeah, I'll do that. I think that's a useful thing to do. Okay. So yeah, you can see the Jamboard, right? Okay, good. So, okay, let me start with a recap of Deutsch's algorithm, and I think it'll be very useful to go through the calculations. So here's a recap. So we have a function, we're given sort of black box access to some function f. It's a function from a single bit mapping to a single bit. And we discussed a lot what it means for us to get black box access. In the quantum case, black box access means we get to invoke the unitary u sub f once. Okay, and u sub f is a unitary which maps x, y, so it's a unitary on 2 qubits, quantum gate on 2 qubits. It maps xy to x, y plus f of x. And remember, we had argued that in the classical case, if I were given access to a black box access to a function that x in a similar way, sort of on the standard basis, right? If I'm classically given a function that allows me to get this, then we had argued that this doesn't really allow me to determine whether f is constant or balanced using a single query. Classically, even with access to this, I still need 2 queries because any single query that I make, I will choose a particular x, right? And I will only ever get information about f of x, but not about the other value. To determine whether the function is constant or balanced, I need information about both. Okay. So here is a recap of the algorithm, of Deutsch's algorithm. So you start by preparing the first qubit in a superposition in the plus state, and the second qubit also in a superposition in the minus state. Okay. Actually, let me take a step back. I think now it will be quicker because you've seen it already. So let me go through kind of the thought process for Deutsch's algorithm first, and then we'll see the actual algorithm itself. Okay. So the first thought was, if I start by putting the first qubit in superposition, okay, so I prepare, for instance, this state here. Okay, so this is, 1 over square root of 2, 0, plus 1 over square root of 2, 1. And you can stop me, whenever something is unclear. So here's first qubit in superposition. Now, if I then apply sort of UF to this, what I get is, UF, sorry, oops, applied to plus 0, which is, UF. Okay, this state here, you can write as, just by distributing things, you can write it as 0, 0, plus 1 over square root of 2, 1, 0. So I plug it in at the bottom. And so now by linearity, I can just act with UF on here and UF on here and sum the two things. So this is the same as this. Okay. And by the definition of UF here, okay, what I get is, because the second qubit is in the 0 state, I simply get 1 over square root of 2, 0, f of 0, plus 1 over square root of 2, 1, f of 1. So far, so good. Should I clarify anything? How does everyone feel about this? The plus is the plus. Let me write it at the top. The plus is 1 over square root of 2, 0 plus 1. You can see it at the top, right? Mm-hmm. And so if I put the first qubit in superposition, then what I end up with after applying U sub f is a superposition of f of 0 and f of 1. But if I do measure, I get, each of them with 50% chance. I don't actually get information about both simultaneously. Okay. So the second approach that we had seen instead was, okay, I can use colors. Let's see. Nice. The second approach was to put the second qubit in superposition. Okay. And now, so instead I will start with the state 0 minus, okay, where minus is, let me put it also here at the top, minus is 1 over square root of 2, 0 minus 1. Okay. So now this state here is the same as, I can expand things out, 0, then 1 over square root of 2, 0 minus 1. Okay. If I sort of apply the distributive property, this is going to be 1 over square root of 2, 0, 0, minus 1 over square root of 2, 0, 1. Okay. And now let's apply UF and see what happens here. Let's apply U sub f to this state here, right? again, by linearity, it's as if I'm acting, separately on each branch. Okay, so what I end up with is 1 over square root of 2 u sub f 0, 0 minus 1 over square root of 2 u sub f 0, 1. Okay. And we can apply the definition of u sub f again. What this gives us is, 1 over square root of 2. Here we have, sorry, oops. We have 0 f of 0. And here we have minus 1 over square root of 2, 0, and then 1 plus f of 0. Okay. Now, unfortunately, I have to turn the page. I have to turn the page, unfortunately. Let me first make a modification here. So let me, the first qubit here, let me start it in the state x. Okay, let's be a little bit more general. Let's not restrict ourselves to starting it in 0. So the first qubit can be x. Okay, either 0 or 1. Okay, I'm just changing the first qubit everywhere. Then it will be f of x. And here, finally, we will have x and f of x. Okay. So far, so good. Just confirming that we're all good so far. Okay. Okay, so I'm gonna copy this expression to the right, to the next slide. I'm going to the next slide. Okay, so what we have at the bottom just now was 1 over square root of 2 x f of x, okay, minus 1 over square root of 2 x 1 plus f of x. I just copied what we had just now. Okay, and you can write this, by, the first qubit is always in the state x, so I can sort of factor it out. So this would be x, okay, and then 1 over square root of 2 f of x minus 1 over square root of 2 1 plus f of x. Is f of 0 equals 0 parity? Sorry, what do you mean by that question? Could you help me clarify? So in the
one side before you had
one side before.
Yes, yes. Well, when you had plus and 0, and the result of this was yes, and result of this is f0, and not why there is no like parity symbol somewhere, because uf is maps to x and parity
yes.
fx.
Yes,
I don't get it.
I see. So I see what you're saying. So it should be, right, by definition of u sub f, as you're saying, it should be y, right, XOR f of x, right?
Yes.
Yes, but the second qubit here, the y qubit in this top case here is 0. So now I understand your question. So it's actually, this is 0 XOR f of 0. And here it should be 0 XOR f of 1.
Okay.
But if you XOR 0 to anything, the parity doesn't change. So that's why it's the same as saying f of 0, f of 1.
Okay, I think I get it. So I don't know.
Yeah.
If,
No. So
can you repeat?
Yeah. So it's absolutely correct what you say, that it should be 0, XOR with f of 0.
Yeah.
Like this, yeah. But 0 XOR f of 0 is equal to f of 0.
Ah, okay. So it's like I was saying on the chat.
Yeah, it's exactly how you were saying.
Okay.
Yeah. So the adding the 0 like doesn't, XORing with 0 doesn't change the parity, and so that's why I didn't write it. But yeah, you're correct. So for both, f of 0 and f of 1, there is a XOR with 0. That's it's exactly as you say. Okay, so then this state here, we had noticed yesterday that it's actually equal. I mean, what you can show is that it's actually equal to this state here. Is this too big of a leap to make? Or are people happy with this leap? The reasoning is that, I mean, this state here, okay, right? One of the cats is going to be 0. The other one is going to be 1, right? Because they differ by 1, right? So this state here is either, 0 minus 1 or 1 minus 0, okay? In other words, which is minus 0 minus 1, right? So it's always going to be at 0 minus 1, except that there is a minus 1 phase, a minus 1 factor at the front. Whether there is or there isn't depends on the value of f of x. If f of x is 0, then we're in this case here, 0 minus 1. And if f of x is 1, we're in the 1 minus 0 case, in which the minus 1 factor appears. But other than the square root 2, it makes sense. Good. So basically, what we deduce from this second case here of the second qubit being in superposition. Let me just rewrite what I had in the previous bullet point. So second qubit in superposition. What we just deduced with this calculation is that, if I apply u sub f to the state x minus, what I end up with is minus 1 to the f of x, x minus. Okay, so this is the equation to remember. Let me color it differently. Okay. Let me also, I don't know how do I bring this to the next slide, if there's a way to cut it. Okay. Anyways, so now what does Deutsch's algorithm do? I mean, this putting the second qubit in superposition just by itself, it does not really allow us to solve the problem, because this minus 1 to the f of x is a global phase. So as you remember, this doesn't, it's not detectable by a measurement, okay? So the key in Deutsch's algorithm was to do both approaches at the same time, put the first qubit and the second qubit in superposition, okay? So instead of starting with x minus or plus 0, we will put both of them in superposition, okay? So we will do the following in the next slide, okay? So we will start, so this is Deutsch's algorithm. We will start with plus on the first qubit and minus on the second qubit. Okay. So let's write it as, let's open up the first plus. Okay, so it's this state and then minus. Okay. Now what happens if I apply U sub f? If I apply U sub f, it's gonna, okay, let me first write what we have here in a more convenient form. So let me say it's 0 minus plus 1 over square root of 2, 1 minus. Okay, I'm just breaking up what I had above. Okay. And now I apply U sub f. Let's see what we get. Right now, UF is going to act separately on the two terms, right? So what I get is 1 over square root of 2 U sub f 0 minus plus 1 over square root of 2 U sub f 1 minus. Okay, and now I can sort of import the calculation in blue that we showed on the previous slide. Let me rewrite it. We had shown in the previous slide that UF applied to x minus equals minus 1 to the f of x, x minus. Okay, so this is what we had shown on the previous slide. Okay. And so we can just apply this equation. Sorry, there are questions. So what is use of f? Use of f. Sorry, did I write? So is this that I didn't write it properly? I mean U sub f. Okay, sorry. What I'm saying, whenever I'm saying U sub f, I'm saying sub for subscript. If it's better, I can call it UF. Sorry for the confusion. When I say U sub f, I always mean this unitary gate here. Sub f is for subscript f. Okay. Okay, and so now if we apply this equation in blue, which was what we calculated in the previous slide, we're going to use it here and we're going to use it here, right? So what we get is just using the equation. So let's pull out the 1 over square root of 2 at the front. Okay, we have minus 1 to the f of 0, and then 0 minus. And here we have 1 over square root of 2 minus 1 to the f of 1, 1 minus. Okay. And now we're almost there. Okay. Let's multiply everything by a global phase of minus 1 to the f of 0. Remember, global phases, they don't really matter, right? They don't change the state. It's the same state. If up to a global phase, it's the same state. So let me I can freely multiply by -1 to the f of 0. Okay, so I'm gonna say this is equivalent to multiplying by -1 to the f of 0. Okay. Okay, and this now, okay, this quantity here, you should be able to realize that it's equal to 1, right? It's either -1 times -1 or +1 times +1. It's equal to 1. Okay, and then this quantity here, this other quantity here, this -1, oh, that's very bad. I want to say this quantity here, okay, that's -1 to the f of 0 plus f of 1. Okay, so all in all, what we get is 1 over square root of 2, 0, minus plus 1 over square root of 2, and there is a -1 to the f of 0 plus f of 1, and 1 minus. Okay, so now at this point, the second qubit is returned to the state minus. We don't need it anymore. Okay, this last quantity that we got here, let me highlight it. This quantity here, I'm going to rewrite it on the next slide. We can ignore or factor out the second qubit. Factoring out the second qubit, what we get is just 0 plus -1 to the f of 0 plus f of 1, 1. And then there's this minus in the second qubit that we can ignore. And now the very last thing to realize is that this quantity here, this state here in the first qubit, it's actually, equal to plus if f of 0 plus f of 1 is equal to 0, is equal to minus if f of 0 plus f of 1 is equal to 1. Okay. And recall that f is balanced, so f is constant. If the XOR of f of 0 and f of 1 is 0, right? And f is balanced otherwise. This is what we had also discussed yesterday, right? So the XOR of two things is 0 if they are the same, and the XOR is 1 if the two bits are different. Okay. So this quantity f of 0 plus f of 1 is precisely the solution to our problem. Okay, if it is 0, we ended up with the plus state. If it was 1, we ended up with the minus state. And then recall also that we can distinguish plus from minus by applying a Hadamard gate. Okay, so the last thing that we do is we apply a Hadamard gate to the first qubit. And if the, if we're sort of, we end up with the qubit in state 0, it meant that we had a plus, so the function is constant. If we end up with the first qubit being in state 1, it means that we had a ket minus, and so the function was balanced. So this is the algorithm. That's it. You prepare ket plus, ket minus. That's how you start your algorithm. You make one invocation to U, to this unitary U sub f, and you end up by doing a final Hadamard on the first qubit, and then you measure. Check if you get outcome 0 or outcome 1, and that's the solution to your problem.